So in the last part of this lecture, we're going to look at the SCP common mode gain. So let's look at our common mode circuit. We'll draw it similarly to our small signal circuit for the differential mode gain that we drew. Only we're going to put a common mode voltage in, which means we're going to put a VIC in. We're going to measure the output differentially, VOC. And remember, ideally, we'd like to see nothing come out for our common mode input. Now we know that half of this tail current source, IS, goes through one transistor and the other half goes through the other transistor. So knowing that, we can actually split this current source up into two independent current sources, half of which feeds transistor M1 and half of which feeds transistor M2. So we're going to redraw this like so. We take our half circuit, break our current source up into two independent current sources. Our resistance, of course, would be in parallel, so we would need 2 RS in order for the circuit to be equivalent. IS over 2 here. 2 RS here. Alright, so this is an equivalent circuit for what we just drew here. Alright, well, what we see here is we have another case where we have a half circuit. And remember, in our half circuit analysis, our in our small signal analysis, our DC current source should be equal to 0. So we can redraw at least one half of this circuit, like so. Alright, so now we need to find our total voltage gain, AV, which is equal to, of course, GM times R total at the output. And we know big GM here is equal to little gm divided by 1 plus GM plus GMB times the resistance that we see in the source, which is 2 RS. We know that our R total is approximately equal to RD because the output resistance of the transistor would be quite large. And so we can calculate our common mode voltage gain, which is just equal to this AV that we're defining here, is equal to minus GM times RD divided by 1 plus GM times 2 RS. Now here we're just saying that the backgate transconductance is approximately 0, so we're ignoring that. Now remember that our differential mode gain was equal to minus GM times RD, and so our common mode rejection ratio, CMRR, was equal to our differential mode gain divided by our common mode gain, which is equal to 1 plus GM times 2 RS, or whatever the resistance is from the current source. So an ideal current source, of course, would see RS go to infinity. And if RS went to infinity, then the CMRR would have to go to infinity. And this is kind of the result we want. We'd like to have an infinite common mode rejection ratio. We'd like to have some voltage output due to a differential signal and 0 voltage out due to a common mode signal, and that would result in an infinite common mode rejection ratio. Now, all of this is only true if transistor M1 exactly matches M2, the drain resistances exactly match one another, and the input voltages to the signal or to the amplifier are perfectly differential. What we're going to find out, of course, is that that's not likely to happen if we were to build this, and so we will see that our common mode rejection ratio would not be infinite. So what we'll look at in the next lecture is what happens if we don't have these matching conditions between M1 and M2 and the drain resistances don't exactly match.